50 meters beneath the fields outside Geneva, a perfect ring of metal hums at a temperature colder than deep space. Inside it, two hair-thin currents of protons sprint in opposite directions, so fast they circle the 27-kilometer tunnel more than 11,000 times every second. When those currents are nudged to cross, space itself becomes a foundry. Energy concentrates. Quarks and gluons rip free. New particles, some that existed only for a breath after the Big Bang, flash into being and vanish again. This is the Large Hadron Collider. And the real question isn't, what can it break? It's, what can it reveal? We built a 27-kilometer atom smasher because nature hides its deepest rules behind energies our everyday world never reaches. A snowflake can tell you that water freezes, but it won't teach you quantum mechanics. In the same way, a light bulb can teach you electricity, but not why particles have mass, or why matter outweighs antimatter in the universe. To ask those questions, you must recreate a tiny piece of the early cosmos, densities and temperatures so extreme that ordinary matter dissolves into its most fundamental ingredients. An accelerator is the only honest way humans know to do that on command. Why a ring so large? Because energy bends. A proton in a magnetic field curves the way a car hugs a turn. The stronger the magnets, the tighter you can steer. The bigger the ring, the gentler the turn, and the higher the speed you can reach without the protons slamming into the wall of physics. With superconducting magnets around 8 Tesla strong, a circumference of roughly 27 kilometers is the sweet spot that lets the LHC push protons to trillions of electron volts. Think of it like this. If you want to sling a stone faster on a string, you either need stronger arms or a wider circle. CERN chose both, record-strength magnets and a circle that tunnels under 2 countries. The engineering is as audacious as the physics. The beam pipe is an ultra-high vacuum, emptier than interplanetary space, so protons won't bump into leftover gas. Around it sit 1/200 superconducting dipole magnets bathing in liquid helium at 1.9 Kelvin, colder than the cosmic microwave background, so electricity flows without resistance. Each beam is less than a millimeter across, yet carries the kinetic energy of a high-speed train. To keep those trains on track, feedback systems adjust their orbit thousands of times per second. A whisper of misalignment, a fraction of a degree, and the stored energy would quench a magnet or melt metal. The LHC lives on a knife edge, and that edge is controlled down to microns. But smashing is only half the story. You also have to see what you've made. That's where the detectors, Atlas, CMS, LHCb, ALICE come in. Imagine skyscraper-sized digital cameras layered like an onion, silicon pixels at the core to capture tracks from charged particles, calorimeters to weigh their energy, and magnetic fields to curl their paths so we can infer momentum. A single crossing of the beams can create dozens of particles and thousands of sensor hits. Multiply that by 40 million crossings per second, and you understand why the LHC is as much a triumph of computing as of magnets. Custom electronics decide within millionths of a second which collisions look interesting, the rest are discarded forever. What survives streams into vast data farms where algorithms rebuild the invisible, frame by frame, like forensic artists drawing the face of a suspect from a smear of evidence. So what are we looking for? At one level, confirmation. The standard model, the best rulebook we have for the subatomic world, predicts a zoo of particles and interactions. In 2012, the LHC completed that zoo with the Higgs boson, the ripple in a field that permeates all space and gives particles mass. But at a deeper level, we're searching for the cracks in that rulebook. The standard model does not explain dark matter, the cosmic imbalance of matter and antimatter, or why the Higgs itself has the value it has. It is a stunningly accurate map of a continent whose edges we can clearly see. The LHC is a ship designed to nudge past those edges. Energy is the key because of Einstein's famous equivalence, E=mc2. Collisions convert kinetic energy into mass, into heavy, short-lived particles too massive to exist in our cool, slow universe. If a new particle is out there, an extra Higgs cousin, a dark matter candidate, a messenger of a hidden symmetry, high enough energy and enough statistics will make it appear as a bump in the data. We don't dial a particle and order it to show up. We roll the universe's dice at phenomenal speed and watch for patterns that cannot be chance. There's a quieter reason too, one that's easy to miss in the roar of headlines. Building a machine this extreme forces us to conquer problems no one else would pay to solve. How to make kilometers of cable superconduct at 2 degrees above absolute zero. How to run real-time filters on fire hoses of data. How to align detectors the size of cathedrals to the precision of a human hair. The technologies born here escape the tunnel. They become better medical scanners, faster networks, smarter sensors. Even the web you're watching this on began as a way for CERN physicists to share their results. You may have heard the fears, mini black holes, strangelets, a chain reaction that eats the planet. They make great movie plots but terrible physics. Nature performs LHC-grade collisions all the time when high-energy cosmic rays slam into the atmosphere, at energies exceeding what we produce underground. And the Earth is still here. If there were a dangerous process lurking at these scales, the sky would have destroyed us long before we learned to build superconducting magnets. The reality is less apocalyptic and more extraordinary. The LHC is a microscope aimed at the foundations of reality, not a weapon pointed at the world. Yet the most compelling answer to why build it is simpler. Because ignorance is expensive. The universe is not obligated to be intuitive. It hides its rules behind scales we cannot touch with our hands and times we cannot revisit. The cost of not knowing, of living with bad guesses about dark matter, mass, or the symmetries of nature, is a universe closed to explanation. The LHC buys us access. It lets us ask a question in the only language the cosmos will always answer: experiment. Deep underground, the protons continue to circle. In the time you've watched this, they've completed hundreds of thousands of laps. Somewhere, in one of those crossings, a pattern no one has seen before may already be sitting on a hard drive, waiting for the moment a plot on a screen bends upward, just enough to make every physicist in the room stop breathing. That is why we built a 27-kilometer atom smasher, not to end the world, but to discover with embarrassing clarity how it really begins. To reach those outrageous energies, a proton's journey begins humbly. A puff of hydrogen gas donates its electrons, leaving bare protons that are coaxed forward by radio frequency fields, electric waves timed to shove the particles every time they pass. First, a linear accelerator gives them their initial kick, then a relay of circular machines takes over like a space program's launch stages. Each ring hands the beam to the next at a higher energy, culminating in the 27-kilometer tunnel. Only there do the superconducting magnets and radio frequency cavities wind the protons up to a hair's breadth under light speed, where their momentum turns into discovery. Acceleration alone isn't enough. You also need density, lots of protons overlapping at the collision point. Physicists measure the brightness of a collider with a quantity called luminosity, a product of how many particles you cram into each bunch, how tightly you focus them, and how fast you cross them. Higher luminosity means more chances for rare processes to occur. But there's a cost. When two bunches cross, you don't just get one collision, you get tens, sometimes hundreds, stacked on the same camera frame. This pile-up is like trying to identify a whisper in a room full of cheering fans. The detectors and the software have to peel those collisions apart, event by event, to find the one that matters. When beams finally meet inside a detector, the firework lasts a sliver of a trillionth of a second. The electronics cannot ship every spark to disk, so they make ruthless choices. Custom chips examine the spray 40 million times per second, looking for telltale patterns, 2 photon flashes back to back, a quartet of clean lepton tracks, a big imbalance of momentum that might betray an invisible particle escaping the scene. From that torrent, the system saves perhaps 1,000 snapshots per second for deeper analysis, 1 in 40,000. Everything else is discarded forever, and yet even those survivors fill data farms with petabytes every year. The machine is a factory for ignorance reduction. The Higgs discovery is the canonical example of how all this comes together. The boson itself lives for a whisker of a moment before decaying into more familiar particles. 2 clean channels became the beacons. In one, the Higgs decays to 2 photons, a crisp, reconstructible signature that appears as a sharp bump in the spectrum of photon pair energies. In the other, it decays into 2 bosons, which themselves decay into 4 leptons, electrons or muons. 4 immaculate tracks spiraling in the detector with the right angles and energies are so rare that background processes almost never fake them. It took years of collisions and meticulous background modeling for 2 separate experiments, ATLAS and CMS, to see a bump at the same mass, about 125 GeV, with statistical significance beyond 5 sigma, the particle physics gold standard for "this is real." But the collider is more than a Higgs machine. At one end of the ring, LHCb specializes in beauty quarks and their decays, a stage on which the subtle difference between matter and antimatter, CP violation, plays out. The standard model predicts tiny asymmetries. Measuring them with extreme precision tells us whether there is new physics nudging the scales. Down the tunnel, Alice collides heavy ions, lead nuclei, to melt nuclear matter into the quark-gluon plasma, a soup that filled the universe microseconds after the Big Bang. Oddly, this plasma behaves like an almost perfect fluid with vanishing viscosity, swirling and flowing rather than spraying. Inside a single facility, you can watch the infant universe and interrogate the rules that govern today's. Even the environment that keeps the beams on track is a triumph of extremes. The dipole magnets are coils of niobium-titanium cable, miles of it, bathed in superfluid helium at 1.9 Kelvin, so they conduct without resistance. They must be shielded from tiny heat leaks and protected from quenches, sudden losses of superconductivity that can dump the energy of a freight train into a meter of metal. Sensors and valves form a nervous system that reacts in milliseconds to steer energy away and shut down safely. Focusing magnets, quadrupoles, squeeze each proton bunch at the collision point to a spot thinner than a human hair. Radio frequency cavities bunch the particles like beads on a wire and give timed kicks to keep them synchronized. All of this is synchronized to tolerances that would make a watchmaker blush. Outside the collider ring, another campus of experiments pushes different frontiers. In a separate complex, antiprotons are produced and then slowed down, decelerated to almost a standstill. That allows teams to assemble antihydrogen and test whether antimatter falls the same way in Earth's gravity, a deceptively simple question with profound implications. Elsewhere, beams of neutrinos, ghostly particles that pass through light years of lead as if it were fog, are created and sent to detectors hundreds of kilometers away to watch them oscillate between identities. CERN is less a single experiment than an ecosystem where questions at the limits of knowledge can actually be asked. Because the LHC works so well, the next step is not necessarily higher energy, but more collisions. The high-luminosity LHC upgrade retrofits the machine with stronger focusing magnets and novel crab cavities that tilt the particle bunches sideways, increasing their overlap and therefore the odds of a collision. To survive the onslaught of data and radiation, detectors are being torn down and rebuilt with faster, finer pixel layers and electronics that can decide even quicker what to keep. If today's typical collision includes dozens of overlapping interactions, future runs will see well over 100 per crossing. Analyzers must learn to thread needles in haystacks that themselves are inside other haystacks. How do you know when you've actually found something new? Not all discoveries look like a photogenic bump. Some hide as tiny deviations in angular distributions, or as subtle mismatches between predicted and measured rates. Others appear as missing energy, the signature of a neutral particle that doesn't touch the detector at all, perhaps a dark matter candidate slipping through like a ghost. Each analysis is a negotiation between theory and data. Define a region where you expect only background, train your algorithms there, and then peek into the signal region with every bias removed. The discipline is less about eureka moments than about a brutal, methodical elimination of ways you could be fooling yourself. And still the horizon tempts. Designs exist for a next-generation circular collider, roughly 100 kilometers in circumference, with magnets powerful enough to accelerate protons to 10 times today's energies. Other groups sketch muon colliders whose heavier leptons could probe the Higgs sector with surgical precision, albeit with their own engineering nightmares. Whether or not those machines are built will be decided by budgets and political will, but the physics case only grows as the known map's edges sharpen. Each time a current machine squeezes another decimal place of precision or opens another window at higher energy, it either reveals a crack or tightens the constraints, both of which are progress. There is a romance to this work that doesn't quite fit in an equation. Hundreds of people aligning a detector the size of a cathedral to the thickness of a sheet of paper. Midnight control rooms where a tiny line on a plot tilts upward and a murmur runs through the crowd. The quiet confidence that even a null result, if measured well, changes our understanding. Particle physics often advances by ruling out beautiful ideas. That too is discovery. The accusation that this is esoteric, a luxury science, misses the point. Yes, the questions are abstract: mass, symmetry, the vacuum. But the tools forged to answer them build the world we actually live in. Superconducting wire learned here shows up in medical imaging. New algorithms for pattern recognition in detectors soon chase tumors in scans or fraud in markets. Worldwide computing grids pioneered to share collider data became prototypes for the cloud long before the cloud had a name. Curiosity is not just a philosophy, it is infrastructure. In the end, the collider is a mirror as much as a microscope. It reflects a species willing to cooperate across nations and decades to ask a question whose answer no one can predict, but everyone can share. Under the quiet pastures, protons will keep crossing 40 million times per second, while on the surface, people argue about budgets and priorities, as they should. Somewhere in that underground ring, the universe is still deciding what to reveal. And up here, we're learning the patience to listen. Beneath the farmland and the mountains, the ring keeps humming. Each crossing is a question written in energy, each saved event a partial answer. We built this machine to finish an unfinished map. The standard model works spectacularly well until it doesn't. Somewhere in the tails of a distribution, in a rare decay, in a tiny mismatch between prediction and measurement, the next door will open. What might wait there? A clue to dark matter that finally links astronomy to the lab. A new symmetry that explains why matter won the cosmic coin toss. A sharper picture of the Higgs that shows it is not alone. Or perhaps no new peaks at all, only tighter bounds that force theory to grow up. Progress in physics is not just fireworks, it is the quiet narrowing of possibility. And even when the plots look flat, the world above changes. Magnets, detectors, algorithms, and the global collaboration required to run them seep into medicine, computing, and industry. A collider is a factory for knowledge and for tools that outlive the questions that birthed them. In the end, this is the wager, that reality yields to careful questions asked at scale. Protons will keep colliding, patience will keep watching. Not to end the world, but to understand it, one precise collision at a time. That is why we built a 27-kilometer atom smasher.